Let's look at this final theorem in which we have an estimable, better say, linear function of parameters, and we have also unbiased estimator, and we want to look at linear transformations. This theorem says that suppose that the elements of Q prime B is the vector of parameters, are estimable with best estimators of the elements T prime Y is the vector of observations. Then for any vector H, diagonal or column vector H prime Q prime B is estimable, and the best estimator in this case is given by H prime T prime Y. Furthermore, the rank of Q is equal to the rank of T. The proof is pretty simple and straightforward, but before going to the proof, let me give an illustration for this theorem to better understand what it says. Let's open the page, and remember the common example that we carried on through this notes, the y1, y2, y3, which we had it as alpha plus beta minus gamma, second element the same, and the third element sum of all the parameters. Here we can consider that we have two linear functions of parameters. If we consider this one, the first one and the third one, so we can write it this way: alpha plus beta minus gamma and alpha plus beta plus gamma. One may write it as Q1 prime B and Q2 prime B. Once again, remember B is alpha, beta, gamma. So you can consider it as Q prime B. Okay, and furthermore, the estimate we can conclude that the estimator is given by Q prime B hat, which in this case we have Q1 prime B hat and Q2 prime B hat, which gives alpha hat plus beta hat minus gamma hat, and then alpha hat plus beta hat plus gamma hat. Okay, if we solve such linear equations, we can then conclude that beta hat is equal to 0, for instance. Gamma hat is equal to minus 1/4 y1, minus 1/4 y2, and then half y3. And then alpha hat, one can get it as 1/4 y1, 4 y2, and then plus half y3. Then we can substitute the estimators, and we can then conclude that alpha hat plus beta hat minus gamma hat is given by half y1 plus half y2, which we can write it in short as y1 plus y2 half. Okay, so we can conclude that the Q prime B hat has this specific form, half y1 plus y2, and the other elements we can easily get y3, and I can of course write it as half element wise this matrix as the coefficient matrix with y1, y2, and y3, which is T prime Y. So the expected value of T prime Y is Q prime B. Here, if you look at this guy, we have a vector which is expressed based on the elements of y. Yeah, this is actually a vector based on the observations. Now let's look at the the function, or better say linear transformation H prime Q prime B. We know that according to the theorem it is estimable with best estimator of exactly the same H prime T prime Y. We want to show it here. Let's look at H prime Q prime B and suppose that it is the sum of the two elements Q prime B plus Q2B. For a moment, suppose H is given by a column vector 1 1. Then you can then the H prime Q prime B is given by Q1 transpose B plus Q2 transpose B. So it is indeed 2 alpha plus 2 beta, which we can write it as 1 1 the Q1 prime B Q2 prime B. Now let's look at the elements of H prime T prime Y. For the elements of H prime T prime Y, we have this row vector 1, and then as above, half 0 0 1, and then the observations. If we do a simple algebra, then it is equal to half y1 plus half y2 plus y3, which is indeed equal to, let me change the color, the color to red, then 2 alpha hat plus 2 beta hat, which you can see it is the estimator of this linear function of parameters. And this is actually an illustration for the theorem. But now let's look at the proof of the theorem. It is pretty simple. Since a linear function is estimable, if it has an unbiased estimator, so you can easily get the expected value of the linear transformation of the best estimator, H prime T hat Y. H prime T hat comes out, and then the expected value we have H prime Q prime B for every TH in the column vector space on X. The expected value of T prime Y indeed is T prime XB, which is Q prime B, and the proof is done. For the rank, consider the rank of the product of two matrices is always smaller or equal to the minimum of the rank of each of the matrices. So I can write the rank of Q as the rank of T prime X, because here the Q prime is equal to T prime X, the rank of Q is equal to the rank of Q prime, so the rank of Q is equal to the rank of T prime X, and it's lesser than the rank of T. Which is then equal to the rank. Then you can see if I have the rank of Q greater than the rank of T, then I can say, okay, in one direction we have lesser or equal to rank of T, in another direction we have greater or equal to rank of T, then it must be equal. Now look at T prime Y. T prime Y is indeed Q prime B hat, and if you replace B hat, then it is equal to Q prime X generalized inverse X prime Y. So we can conclude that T prime is equal to this coefficient of the observation. So T prime is equal to this, and exactly in a similar fashion as above, we can decide that the rank of T is smaller than the rank of Q. So in one direction we have rank of Q is smaller than or equal to rank of T, and the other direction we have rank of T is smaller or equal to rank of Q. So we can decide that the rank of these two matrices are is equal to each other. Now let's look at the covariance matrix of T prime Y, the best estimator of Q prime B. once again, if I write it here, if I have a covariance of let's say a z, z here is random and a is constant, non-random, then it is a covariance of z a prime. So using that, the covariance of t prime y is simply t prime covariance of y t. The covariance of y is equal to sigma square. Remember, it is sigma square identity. Then I replace the t from this equation. So it is given by this formula. We can then replace q from the theorem. Here we have q prime equal to t prime x, and q is equal to x prime t. So if we replace it, then we have the covariance of t prime y based on generalized inverses of x and t. According to the properties of generalized inverse, remember this matrix is idempotent, so I can write it as this expression. And then once again, writing t prime x based on q prime, it is equal to q prime. Here for this I'm using q prime equal to t prime x. And you can find the covariance of t prime y as by this formula. For sure, if there x is of full column rank, which is equal to p, then b is estimable, and the covariance of b hat, the estimator, is given by this formula. Now let's have another illustration for this theorem in order to better understand it. Let's append. Okay, let's go down and append another page. Yes, let's append another page here. Okay. Now we want to consider the covariance of t prime y. Once again, let me write it here. The covariance of t prime y, according to the theorem, it is given by q prime x prime x generalized inverse. Sorry for this transpose notation, and q sigma square. Now let's remember the example once again. The q prime b is indeed alpha plus beta minus gamma, alpha plus beta plus gamma. And the t prime y, as we had it, half 0, 0, 0, 1, with the observations y1, y2, y3. Now let's look at first of all, I want to compute the covariance of t prime y straight without using the theorem. Of course, it is t prime t sigma square, and then I can use the coefficient matrix. First transpose it. No, first the matrix itself, and then the transposing the matrix with sigma square, which is indeed equal to half 0, 0, 1 sigma square. If you look at this matrix here, this matrix is a diagonal matrix, so we can say the functions are uncorrelated. But if we assume normality, if we further assume y has normal distribution, then we can say, okay, the two functions are also independent, and that's interesting. But for the case that the distribution is normal, if it is not normal, we cannot say anything about independency. But on the other hand, we know that the q prime b hat is equal to alpha hat plus beta hat minus gamma hat. And then the covariance of this best estimator is given by q prime x generalized inverse q sigma square according to the theorem. If I write q prime, it is 1 1 minus 1. It's a coefficient, we have it, and then the generalized inverse of x prime x, and then the transposes matrix of q prime sigma square. But the problem arises when we want to compute the x prime x generalized inverse. Indeed, we need to compute this generalized inverse. Just in order to finish this example, for a moment, suppose that in a method, or with one method, I've obtained the generalized inverse, and the generalized inverse is equal to this matrix. Let me write the elements: 0, and then 1/8, 3/8. If we do a little bit of computation, we can easily see that it is equal to, once again, half 0 0 1 sigma square. And it is nothing than the covariance of t prime y. So those are the same. But in order to see how we can get this generalized inverse, let's consider a pretty simple method. The expected value of y, once again, I'll write it as this matrix: 1 1 minus 1, alpha beta gamma. Remember, the expected value of y was the expected value of y1, which was equal to alpha plus beta minus gamma. The second element, the expected value of y2, is equal to alpha plus beta minus gamma. And the third element, the expected value of y3, is equal to alpha plus beta plus gamma. Now let's look at the normal equations. Normal equations for the linear model. For the normal equations, of course, I have the x prime x b hat, which is then 1 1 1 1 1 1 minus 1 1 1 minus 1 1 1 minus 1, and then 1 1 1, and the b hat, which is equal to alpha hat plus beta hat gamma hat, which then I can write it as 3 after a simple matrix multiplication: 3 3 1 minus 1 minus 1 3 alpha hat beta hat gamma hat, and then it is equal to 3 alpha hat plus 3 beta hat minus gamma hat. We have the second element is the same, we expect so, and the third element minus alpha hat minus beta hat plus 3 gamma hat. On the other hand, once again, the right hand side of the normal equations is equal to x prime y, which is then 1 1 1 minus 1 times y1, y2, and y3, which I can write it as y1 plus y2 plus y3. The second element the same, and then the third element plus y3. Let me assume that I use the notation or the or whatever you call it as y1, y2, y3. Then I can say, okay, the second row is the same as the first row, so instead of y2 I can even write it y1, and so instead of y3 I can write y2, because then I have 2 elements here. So I denote the sum of observation as y1 and this summation as y2, just to simplify the writing on for the solution. Okay, remember the solution, set beta hat equal to 0. Then from the first row I can conclude that alpha hat is equal to 1/3 gamma hat plus y1 plus y2 plus y3, which I can represent it as 1/3 gamma hat plus y1, capital Y1. From in a similar fashion, I don't want to go through details in order to compute. We can conclude that 2 alpha hat plus 2 gamma hat is equal to y1, capital Y1 plus capital Y2, and also for gamma hat. Sorry, let me write it better. The gamma hat, it is then equal to y1, half y1 plus y2 minus 1/3 gamma hat plus y1. It comes from alpha hat. So we can conclude that 4/3 gamma hat is equal to half y1, capital Y1 plus half y2, minus 1/3 y1, capital Y1, which we can write it as 1/6 y1 plus half y2. And similarly, we can find alpha hat, which is then 3/8 y1 plus 1/8 y2. These are capital Y1, capital Y2. But let me use another color. But remember, b hat is equal to x prime x generalized inverse x prime y, and I can use this. I can then use it and write. We can conclude that alpha hat plus beta hat plus gamma hat is equal to, let's do the multiplication, 3/8 y1 plus 1/8 y2, here 1/8 y1, capital Y1 plus 3/8 y2, and the second element is equal to 0. We know that it is equal to x prime x generalized inverse. Let me use the previous color, x prime y. But if you look at x prime y, it is nothing than so the solution is, let me use the first, let me write it here. The solution is a matrix multiplied by x prime y. X prime y is nothing than y1, y2, it is of course x prime y is here, it is y1, y1, y2. So I can write it as y1, y1, y2. And then if you compare it with above, you can simply see that, okay, this is the required matrix. Let me do the let me a little bit minimize it. Okay. Then we can then from here we can come to this point, and you see we could easily get the result. Okay, and I stop the video here, and in another video I will record the the examples. Thank you